Okay, let's be honest. Staring down an honors chemistry final, it kind of feels like standing at the base of a mountain, right? And your map is made of like 1,000 pieces of paper, all your articles, notes, research scattered everywhere. It's not just a lot. It can feel really overwhelming.
Absolutely. Trying to synthesize that much information, especially, for a big comprehensive exam,
Yeah.
it can seem almost impossible. You've got to find the core ideas, the stuff that really fits together.
And that's exactly what we're going to try and do right now, just for you. You've gathered this stack of sources, and we're going to deep dive into that material, and only that material. Our mission, it's pretty simple. We're going to be your guides, cut through all that information overload, pull out the most important nuggets, connect the dots, and give you a much clearer picture of what you really need to get a handle on for that final.
Yeah, think of this as your personal curated shortcut. We're extracting the essential knowledge and helping you see how it all connects, pulling directly from the material you shared with us.
Perfect. Okay, let's start at the very beginning with the fundamental idea that everything around us is, well, chemistry. Your sources really make a point of saying that chemicals aren't just, scary things in a lab coat's pocket. They literally make up everything we encounter.
That's totally right. From the air we breathe, the water we drink, to just everyday things like toothpaste or even the paper these notes are on. It's all chemicals and chemistry. That's the study that helps us understand the properties and behavior of all this stuff by looking right down at the molecules they're made of.
So all this stuff is matter, and matter exists in different states, solid, liquid, gas. Is there a key property that differentiates these states that your sources zeroed in on?
Well, one property that's a really clear differentiator, especially thinking about gases, is compressibility. Gases are, well, highly compressible simply because their particles are so far apart, there's loads of empty space between them.
Right.
So you can easily squeeze them closer together, like, pumping air into a bicycle tire. Liquids and solids, their particles are packed way closer, so they're much, much less compressible.
Okay, so matter has states. Got it. But matter itself isn't all the same, right? We classify it.
Precisely. We make a big distinction between pure substances and mixtures. A pure substance is either an element, something you can't break down into simpler stuff by chemical means, think carbon, gold, nickel,
Okay.
or it's a compound. It's made of two or more elements chemically bonded together in a fixed ratio. Baking sodium bicarbonate, that's a classic compound example from your notes.
And mixtures are just different substances physically mixed, not chemically bonded.
Exactly, not chemically bonded. And mixtures themselves can be homogeneous, meaning they look uniform throughout. You can't see the different parts like sugar dissolved in water or even clean air. Or they can be heterogeneous, where the composition isn't uniform, and you can see distinct parts, think of like a bowl of soup or rocky road ice cream, or even cloudy air, as your sources mention. Helium gas is pure, an element. Concrete is heterogeneous.
And matter changes. We need to be clear on physical versus chemical changes. This seems important.
Definitely. A physical change just alters the form or appearance, but it doesn't change the chemical identity.
Yeah.
Sugar dissolving in water, it's still sugar, it's still water, just mixed. That's physical.
But if I, say, burn that sugar, that's total different.
Absolutely. Burning sugar creates new substances. Ash, carbon dioxide, water vapor. That's a chemical change. Involves a chemical reaction, altering the molecules themselves. Copper turning green when it's left outside. Another chemical change mentioned.
Right. Okay, so to understand all this matter and its changes, we obviously need to measure things. And a really fundamental point your sources make is that any measurement needs two things. Always.
Always. A number and a unit. A number without a unit is, well, pretty much meaningless in science. If I say 10 is at 10 meters,
Yeah.
10 grams, 10 seconds, the unit gives it context and meaning.
And the metric system is key here, obviously. Your sources spend a good chunk of time on unit conversions. Looks like a skill you really need to nail.
Oh, it's critical. And the approach is really systematic. You start with your given quantity and its unit, right? They use conversion factors. These are just ratios of equivalent values that have different units to kind of step-by-step cancel out the units you have and introduce the units you want. Your material shows this for everything from simple stuff like centimeters to inches or meters to kilometers to more complex ones like grams per pound to milligrams per kilogram, where you have to convert both the top and bottom units.
This whole process of measuring accurately also brings up significant figures. Why do we even need sig figs? What's the point?
Well, significant figures are absolutely essential because they tell us about the precision of a measurement.
Mm.
When you write down a number you measured, the number of sig figs shows how many digits you're actually confident in, plus one digit that's estimated, or, a best guess. That's why the rules for counting them are so specific. They reflect how good the measurement was.
Okay, so hit us with the basic rules for counting them. How do we know how many sig figs a number has?
All right, so any non-zero digit, always significant, easy. Zeros that are between non-zero digits, also always significant. Now, trailing zeros, the ones at the very end of a number, they're significant only if there's a decimal point written somewhere in the number.
Ah, okay.
But leading zeros, the ones at the beginning, before the first non-zero digit, like in 0.000250, they are never significant. They're just placeholders showing where the decimal point goes. So 58.31.
Right.
4 sig figs, that 0.0002 or Q50. 3 sig fig, the leading zeros don't count, but that trailing zero does because of the decimal point. And something like 100.00 has 5 sig figs.
What about a number like, say, 100,000? My sources mentioned some ambiguity there.
Yes, exactly. That's ambiguous because you just don't know if those trailing zeros were actually measured digits or if they're just there to show the size of the number. Was it measured to the nearest 10,000 or the nearest one? Scientific notation completely clears this up. Writing it as 1 by 105 means 1 sig fig, but 1.000000 by 105 clearly means 6 sig figs.
And these rules, they don't just disappear when you start calculating. You have to track them.
Oh, absolutely. They follow you right into calculations. When you add or subtract, your answer can't be more precise than the least precise measurement you started with, meaning it's limited by the fewest decimal places. When you multiply or divide, your answer is limited by the measurement with the fewest total significant figures. Your sources have examples showing exactly how to apply these. And reading lab equipment like a graduated cylinder or even a digital scale relates directly here. For things with scale marks, you read all the digits you're certain of and then estimate one more digit between the marks. That estimated digit is the last significant figure.
Got it. Another really important quantitative concept is density.
Right, density. It's defined simply as mass per unit volume, mass divided by volume. It's what we call an intensive property, meaning it's inherent to the substance itself. It doesn't matter how much of it you have.
Okay.
You calculate it by dividing the mass by the volume, like in those glycerol or aluminum engine block examples in your notes. But what's really cool and useful is that density then becomes a super powerful conversion factor. It lets you convert between the mass of a substance and its volume, like in that problem converting kilograms of something to its volume in cubic centimeters using its known density.
And all this data we measure, it often ends up in graphs, right? Visualizing the information.
Graphs are such essential tools in science. They let us see patterns, trends, relationships in data that might be hidden in just a table of numbers. Your sources specifically highlight interpreting graphs, using that atmospheric carbon dioxide example. You need to be comfortable reading the axes, finding the value on one axis corresponding to a value on the other, calculating changes between points, and even figuring out a rate of change, which is basically the slope of the graph. It's about pulling the story out of the visual data.
Okay, so that's how we describe and measure the big picture world around us. Let's zoom way, way in now, down to the fundamental building block, the atom.
Right. The sources kind of walk us through how our picture of the atom evolved over time. Started with early ideas like Thomson's plum pudding model.
Ah, yes, the plum pudding, where the atom was just sort of a positively charged blob with negative electrons stuck in it like plums.
Pretty much, yeah. Mass and charge all spread out. But then came Rutherford and his gold foil experiment. He shot these tiny positive alpha particles at a super thin sheet of gold foil, expecting them to just, breeze right through that pudding.
But they didn't. Some bounced back.
Exactly. Most went straight through, as expected. But some were deflected at really large angles, and a few even came straight back. Rutherford himself said it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Just astonishing results.
And that completely changed the model, led to the nuclear theory of the atom.
Totally overturned the plum pudding idea. Rutherford proposed that almost all the atom's positive charge and almost all its mass must be crammed into this tiny, incredibly dense core at the center, the nucleus, the negatively charged electrons. They must be orbiting this nucleus in the vast, mostly empty space that makes up the rest of the atom's volume.
Okay, so the atom has this structure with a nucleus and electrons. What are the key subatomic particles again?
The three main players you need to know are protons, neutrons, and electrons. Protons have a positive charge, plus 1 relative charge, and they live inside the nucleus. Neutrons have no charge, 0 charge, and they also live in the nucleus. Electrons have a negative charge, minus 1 relative charge, and they're found in the space outside the nucleus. And yeah, the nucleus, with the protons and neutrons, contains almost all the mass of the atom.
What determines which element an atom actually is?
That's solely defined by the number of protons in the nucleus. That number is the element's atomic number, usually represented by Z. Change the number of protons, you literally change the element.
Okay, Z is protons. What's the mass number A?
The mass number A is the total count of protons plus neutrons in the nucleus of one specific atom.
Which brings us neatly to isotopes. Because atoms of the same element don't always have the same mass number.
Exactly right. Isotopes are atoms of the same element, so they have the same atomic number, the same number of protons, but they have different numbers of neutrons. And since neutrons have mass, this means isotopes of an element have different mass numbers.
Like the neon isotopes mentioned in the sources, Ni-20, Ni-21, Ni-22, all are neon, so all have 10 protons.
Right, but Ni-20 has 10 neutrons, 10 plus 10 20s. Ni-21 has 11 neutrons, 10 plus 11 21. And Ni-22 has 12 neutrons, 10 plus 12 22. The notation usually shows the mass number, either as a superscript before the symbol, like Feria, or after a hyphen, Ni-20.
And you can figure out protons and neutrons from that notation.
Yep, the atomic number Z, which you get from the periodic table for the element symbol, tells you the number of protons. Then the mass number A minus the atomic number Z gives you the number of neutrons. AZ equals neutrons. Your potassium-39 example works perfectly. K is element 19, so 19 protons. Mass number is 39, so neutrons equals 39, 19 equals 20.
Quick question, if a neutron doesn't have a charge, why is it so important? What does it do?
That's a great question. While it doesn't affect the element's identity like protons do, or balance the electron charge, neutrons are absolute critical. They contribute significantly to the atom's mass, which is how we distinguish isotopes. And importantly, the number of neutrons affects the stability of the nucleus itself. Too many or too few can make a nucleus unstable and radioactive, so they play a huge role in nuclear structure and stability.
Okay, let's talk about the electrons outside the nucleus. The sources mention the Bohr model first, with energy levels.
Right. Niels Bohr proposed a model where electrons didn't just orbit randomly, but existed in specific fixed energy levels or orbits around the nucleus, kind of like planets around the sun, but only certain orbits were allowed. A key idea was that electrons could jump between these allowed energy levels.
And what happens when they jump? Does something visible occur?
Yes. If an electron absorbs the right amount of energy, like from heat or light, it can jump up to a higher energy level, a less stable, excited state. But it doesn't stay there long. When it falls back down to a lower, more stable energy level, its ground state, it has to release that extra energy. It often does this by emitting a photon of light. And since only specific jumps between specific energy levels are allowed, only specific amounts of energy, meaning specific frequencies or colors of light, are emitted. This explained the distinct lines seen in the emission spectra of elements, like the hydrogen spectrum mentioned in your notes.
But the Bohr model wasn't the final word, right? It led to the more complex quantum mechanical model.
Exactly. Bohr's model worked great for hydrogen, but had problems with more complex atoms. The quantum mechanical model replaces Bohr's fixed orbits with something called orbitals. An orbital isn't a path. It's a region of space around the nucleus where there's a high probability of finding a particular electron. Think of it like a probability map or cloud.
And these orbitals, they're organized within the energy levels.
Yes. The principal energy levels, or shells, are numbered N1, 2, 3, and so on, getting further from the nucleus. Within each shell N, there are N types of subshells designated by letters, S, P, D, and F. Your sources mention that S orbitals have a spherical shape.
And each type of subshell can hold a certain maximum number of electrons.
Correct. An S subshell, which contains just one S orbital, can hold a maximum of 2 electrons. A P subshell containing 3 P orbitals holds up to 6 electrons. A D subshell, 5 D orbitals, holds up to 10. And an F subshell, 7 F orbitals, holds up to 14.
And there's a rule for how electrons fill these orbitals, right? They don't just go in randomly.
Right. It follows the Aufbau principle, which basically says electrons fill the lowest energy orbitals available first before moving up to higher energy orbitals. Your sources show the general filling order: 1s, then 2s, then 2p, then 3s, 3p, then 4s, then 3rd, and so on. It gets a little complex, but there's a predictable pattern.
And we use electron configurations and orbital diagrams to, write down this arrangement.
Exactly. They're the chemical shorthand. An electron configuration lists the subshells and how many electrons are in each, like 1 2 S, S2 POA. An orbital diagram goes a step further. using boxes to represent individual orbitals and arrows to represent the electrons within them, also showing their spin. Your phosphorus example shows this visually. Being able to draw these, or at least interpret them, is really key to understanding electron arrangement.
This detailed understanding of electron arrangement, especially those outer electrons, is precisely what allows us to make sense of the periodic table, isn't it?
Absolutely. The periodic table is arguably one of the most powerful tools in chemistry. Its initial organization we owe a lot to chemists like Mendeleev and Meyer, who noticed that when elements were arranged by increasing atomic mass, Mendeleev primarily, certain properties seemed to recur periodically. The modern table orders elements strictly by increasing the number of protons, and this ordering naturally aligns elements with similar outer electron configurations into the same vertical columns, which explains why they have similar chemical properties.
It's arranged in rows, called periods, and columns, called groups.
And an element's position tells you a ton of information. The period number, the row, tells you the principal energy level N of the outermost electrons, the valence electrons. The group number, the column, especially for main group elements, often tells you the number of valence electrons. And its general location, left, right, middle, identifies it as a metal, non-metal, or one of the metalloids in between. Your source also mentioned the S, P, D, and F blocks, which correspond to which subshell is being filled for the outermost electrons.
And some of those groups have specific family names.
Yes, there are several important ones to know. The alkali metals are group 1, very reactive metals. The alkaline earth metals are group 2, also reactive metals, but slightly less so. The halogens are group 17, very reactive nonmetals. And the noble gases are group 18, notably inert or unreactive gases. Your sources highlight these key groups and their general reactivity.
You mentioned valence electrons, those outermost ones. This concept seems absolutely crucial for bonding, right? And something called the octet rule.
Central, absolutely central. Valence electrons are the electrons in the highest occupied principal energy level, the outermost shell. They are the ones directly involved in forming chemical bonds. And the octet rule is the observation or driving principle that atoms tend to gain, lose, or share these valence electrons in order to achieve a stable electron configuration with 8 valence electrons, just like the noble gases, except for hydrogen and helium, which aim for 2, the duet rule.
So an element's electron configuration, specifically its valence electron configuration, dictates how it will react.
Precisely. It determines its chemical behavior. Look at the alkali metals in group 1 again. They all have 1 valence electron and an S configuration. It's energetically much easier for them to lose that single electron to get down to the stable configuration of the previous noble gas. That's why they readily form +1 ions and are so reactive. Now look at the halogens in group 17. They have 7 valence electrons, NSMP. They're just 1 electron short of a stable octet. So it's much easier for them to gain 1 electron to complete that octet, forming a NOC1 ion. This makes them highly reactive as well. And the noble gases, they already have the stable octet, NSNP, so they have very little tendency to gain, lose, or share electrons. Hence, they're inert.
The periodic table also shows us how certain properties change in predictable ways as you move across or down. These are the periodic trends. Electronegativity is a big one.
Electronegativity, yeah. That's a measure of how strongly an atom attracts shared electrons towards itself when it's in a chemical bond. Your sources show it generally increases as you go across a period from left to right and decreases as you go down a group from top to bottom. Fluorine is the most electronegative element.
What about atomic radius, just the size of the atom?
Atomic size actually decreases as you go across a period. This might seem counterintuitive because you're adding electrons, but you're also adding protons to the nucleus, increasing the positive charge, which pulls the electron shells in tighter. As you go down a group, however, atomic size increases because you're adding electrons to entirely new, higher energy shells that are naturally farther from the nucleus.
Okay, that makes sense. And ionization energy, the energy needed to remove an electron.
Right. Ionization energy generally increases as you go across a period. Those electrons are being held more tightly by the increasing nuclear charge. And it decreases as you go down a group. Why? Because the outermost electron is in a higher energy shell, farther from the nucleus, and shielded by inner electrons, so it's held less tightly and easier to remove. Understanding these trends is fundamental for predicting how elements will interact chemically.
All this talk of valence electrons, octets, and achieving stability leads us straight into how atoms actually connect chemical bonding.
Yeah, and the octet rule is really the key driver here. Atoms form bonds they connect with other atoms specifically by transferring or sharing their valence electrons in ways that allow each atom, usually, to achieve that stable outer shell configuration of 8 electrons. Lewis structures, which we mentioned, are the diagrams that help us visualize this. They show the valence electrons as dots around the element symbol and use lines to show shared pairs and bonds, illustrating how the octet or duet rule is satisfied. You should definitely be comfortable drawing Lewis structures for simple molecules and ions.
And there are different kinds of bonds within a molecule, right? The strong connections holding the atoms together. We call those intramolecular forces.
Right. The two main types are ionic and covalent. Ionic bonds typically form between a metal and a nonmetal. It involves a complete transfer of one or more electrons from the metal atom, which becomes a positive ion, cation, to the nonmetal atom, which becomes a negative ion, an anion.
So you get ions, positive and negative.
Exactly. And these oppositely charged ions are then held together by a strong electrostatic attraction, the ionic bond. Think back to Coulomb's law. The force is stronger when the charges are larger and the distance between them is smaller. This strong attraction is why ionic compounds form crystal lattices and have high melting points. It's related to the crystal lattice energy, the energy released when the ions come together to form the solid. Comparing lattice energies gives an idea of bond strength.
And the properties of these ionic compounds reflect that strong bonding, right?
They do. Ionic compounds are typically hard, brittle solids at room temperature, and a crucial point your sources make. As solids, they do not conduct electricity because the ions are locked rigidly in place within the crystal lattice. However, if you melt the ionic compound or dissolve it in water, the ions become free to move around, and then they can carry electric charge, making the molten liquid or the aqueous solution a good electrical conductor. That image of NaCl dissolving in water with the polar water molecules surrounding and separating the Na+ and Cl ions really illustrates this key property.
Okay, so that's ionic bonds, electron transfer. Covalent bonds are different, forming between nonmetals.
Right. In covalent bonds, electrons aren't transferred, they're shared between the atoms. Both nonmetal atoms typically need to gain electrons to reach an octet, so they achieve stability by sharing pairs of valence electrons. Each shared pair constitutes a covalent bond.
And these covalent bonds, they can be either polar or nonpolar. How do we tell the difference? That seems important for understanding molecular properties.
It's hugely important, and it comes back to electronegativity. The difference in electronegativity between the two bonded atoms tells you how equally those electrons are being shared. If the electronegativity difference is 0 or very small, your source suggests 0.7 or less as a guideline.
Right.
Then the electrons are shared pretty much evenly. This results in a nonpolar covalent bond.
Yeah.
There are no significant partial charges on the atoms. Think of the bond between two identical atoms, like in Cl or H.
But if one atom pulls on the electrons much more strongly, if the electronegativity difference is bigger,
then the sharing is uneven. If the AIN is a larger, say between 0.7 and about 1.7 according to your source, the more electronegative atom pulls the shared electron pair closer to itself. This creates a partial negative charge, symbolized on the more electronegative atom, and a partial positive charge, plus on the less electronegative atom. This type of bond, with uneven sharing and partial charges, is called a polar covalent bond. It essentially creates a dipole within the bond. Your sources also note that, generally speaking, ionic bonds, full charge separation, are stronger chemical bonds than covalent bond sharing.
Okay, so those are the strong bonds within molecules, ionic and covalent, polar and nonpolar. But you also mentioned weaker forces between separate molecules, intermolecular forces, or IMFs.
Yes, and these are absolutely crucial for understanding the physical properties of substances like boiling points and melting points. It's vital to distinguish them. Intramolecular bonds hold atoms together inside a molecule, like the OH bonds within a water molecule. Intermolecular forces are the attractions between different separate molecules, like the attraction between one water molecule and another nearby water molecule. They are generally much weaker than intramolecular bonds.
What types of IMFs are mentioned in the sources? What should we know?
The main types discussed are London dispersion forces, sometimes just called dispersion forces. These are the weakest type and, importantly, they are present in all molecules, polar or nonpolar. They arise from temporary random fluctuations in electron distribution around a molecule, which create temporary instantaneous dipoles that can induce dipoles in neighboring molecules, leading to a weak attraction.
Okay, dispersion forces and everything. What else?
Then there are dipole-bipole forces. These occur only between polar molecules. Because polar molecules have permanent partial positive and partial negative ends, permanent dipoles, the positive end of one molecule is attracted to the negative end of another nearby molecule. This is stronger than dispersion forces for molecules of similar size.
And hydrogen bonds, are they actually bonds?
Ah, good question. The name is a bit misleading. Hydrogen bonds are not true chemical bonds like covalent or ionic bonds. They are actually a special, unusually strong type of dipole intermolecular force. They occur specifically when a hydrogen atom is covalently bonded to a very small, highly electronegative atom, namely nitrogen N, oxygen O, or fluorine F, NAD. That hydrogen is then attracted to a lone pair of electrons on an N, O, or F atom in a neighboring molecule. They're super important in water and biological molecules.
How do these different IMFs affect physical properties like boiling point?
The stronger the intermolecular forces between molecules, the more energy, which means higher temperature, is required to pull those molecules apart and turn the substance from a liquid into a gas, boiling. So stronger IMFs lead to higher boiling points. Your sources give great examples, comparing nonpolar hydrocarbons like CH, CH0. As the molecules get larger, their electron clouds get bigger, the dispersion forces become stronger, and the boiling point steadily increases. Same idea for the noble gases mentioned, KRXERAN. As you go down the group, the atoms get larger, dispersion over forces increase, and boiling point increases. And molecular solids, like ice, held together by strong hydrogen bonds, or dry ice, solid CO held by weaker dispersion forces, owe their solid structure and properties entirely to these IMFs.
So IMFs are about the attraction between molecules, but you mentioned earlier that the actual shape of an individual molecule also matters a lot.
It absolutely does. And the theory that helps us predict molecular shape is called VSEPR theory, that stands for valence shell electron pair repulsion theory. It's a beautifully simple but powerful idea.
Okay, what's the core idea?
It's based on the fact that electron groups around a central atom repel each other because they're all negatively charged. Now, an electron group can be a single bond, a double bond, a triple bond, or even a lone pair of electrons that isn't involved in bonding. VSER says these electron groups will arrange themselves in three-dimensional space around the central atom to get as far apart from each other as possible to minimize those repulsive forces.
How does that arrangement help us figure out the molecule's shape?
Well, the number of electron groups around the central atom determines the basic arrangement of those groups, which we call the electron geometry. For example, your sources give the key case. If there are 4 electron groups around the central atom, they will arrange themselves pointing towards the corners of a tetrahedron to maximize separation. That's the electron geometry. Now, the molecular geometry, or the actual shape of the molecule, describes the arrangement of only the atoms, not necessarily the lone pairs. If all 4 of those electron groups are bonding pairs connecting to other atoms, like in methane, CH, then the molecular shape is also tetrahedral, with bond angles around 109.5 degrees. If some groups are lone pairs, the molecular shape will be different, like bent for water, which also has 4 electron groups around oxygen, but 2 are lone pairs. Your sources also mention 3 electron pairs arranging themselves in a trigonal planar fashion. The basic principle is electron group repulsion dictates the spatial arrangement.
Okay, why is knowing the molecular shape so important? What does it tell us?
This is crucial. The molecular shape, combined with whether the individual bonds within the molecule are polar or nonpolar, determines if the entire molecule has an overall polarity or not.
Right. You mentioned that connection before. How do I put those two pieces together, bond polarity and shape, to figure out the overall molecular polarity?
Your sources lay out a pretty clear 2-step process.
Yeah.
Step 1, look at the bonds within the molecule. Are they polar? You determine this using the electronegativity difference. If there are no polar bonds, the molecule must be nonpolar. Easy. Step 2. If there are polar bonds present, now you have to consider the molecule's 3D geometry, which you get from VSEPR. Ask yourself, are these polar bonds, these bond dipoles, arranged symmetrically around the central atom such that they cancel each other out? Or is the arrangement asymmetrical, meaning the dipoles don't cancel and they add up to give the molecule a net dipole moment?
Oh, okay. Like your example of carbon dioxide, CoUr. It has 2 polar carbon-oxygen double bonds.
Right. Oxygen is more electronegative than carbon.
But the molecule is linear, OCO. So the 2 bond dipoles point in exactly opposite directions and are equal in strength.
So they perfectly cancel each other out. The net dipole moment is 0, and KRO is a nonpolar molecule overall, despite having polar bonds.
But water, HO, also has polar bonds, OH.
Yes, oxygen is much more electronegative than hydrogen.
But water's shape is bent, not linear, it's asymmetrical.
Exactly. Because of the bent shape, due to the 2 lone pairs on the oxygen, according to VSEPR, the 2 OH bond dipoles don't point in opposite directions. They don't cancel out. They add together vectorially to give the water molecule a significant net dipole moment, making water a very polar molecule. Your source material has a table showing how dipoles add or cancel in different geometries. This link between bond polarity via CPR shape and overall molecular polarity is a super important concept. It explains why things dissolve in certain solvents, how molecules interact, so much stuff.
It really is amazing how these fundamental rules about electrons and shape dictate so much about how substances behave. Now, okay, with all these atoms bonding and forming molecules and compounds, we need a systematic way to talk about them. We need a naming system. Chemical shorthand.
Absolutely. Chemistry definitely has its own language, its own shorthand. And your sources provide the rules, the grammar, for naming different types of compounds. The very first step usually is figuring out if you're dealing with an ionic compound or a molecular covalent compound.
And the quick way to tell is often, is there a metal present?
Generally, yeah, that's a good starting point. If the chemical formula contains a metal element, or the polyatomic ammonium ion, Na0, which acts like a metal ion, it's usually classified and named as an ionic compound. If the formula contains only non-metal elements, it's usually molecular, also called covalent and named differently. Your sources give examples like KBr and CuO being ionic, while Cs and P-Povero are molecular.
Okay, so naming ionic compounds. It seems like the rules depend on whether the metal involved always has the same charge or if it can vary.
That's the key distinction. We talk about type I ionic compounds. These involve a metal that essentially always forms an ion with the same predictable charge. These are mainly the metals in group 1, which always form +1 ions, group 2, always +2 ions, and a few others like aluminum, Lt, and zinc, ZnO. For these type I compounds, naming is simple. Just state the name of the metal fascion, followed by the base name of the nonmetal anion, with the ending changed to indriide. Examples include SrClO, strontium chloride, NiO, sodium oxide, MgO, magnesium oxide.
What about metals that can form more than one type of positive ion? Like iron can be Fe or Fe, those are type 2, right?
Exactly. These are type 2 ionic compounds, often involving transition metals. Since the metal can have variable charge, the name must specify which charge it has in that particular compound. So the rule is, name the metal cation, then immediately follow it with its charge written as a Roman numeral in parentheses, and then finish with the non-metal anion name ending in "ide." How do you figure out the Roman numeral? You have to deduce the charge on the metal ion by knowing the total negative charge from the anions it's bonded to, since the overall compound must be electrically neutral.
Okay, that makes sense. And what if the ionic compound contains one of those groups of atoms that act as a single ion, a polyatomic ion?
Good point. If a polyatomic ion is involved, you simply use the known name of that polyatomic ion in the compound's name. So it's the metal cation name, including the Roman numeral if it's a type 2 metal, followed by the name of the polyatomic anion. Or, if the cation is polyatonic, like ammonium NH, you name it first, then the anion. Your sources list common polyatomic ions you likely need to recognize, like sulfate, acetate, ammonium NH, carbonate, and perchlorate, ClO, and give examples like PbSO, lead-2-sulfate, and NH, ammonium carbonate.
All right, so that covers ionic naming. How do we name molecular compounds, the ones made of only nonmetals?
These use a different system based on numerical prefixes to indicate how many atoms of each element are present in one molecule. Your sources list the common prefixes you need: mono 1, D2, tri 3, tetra 4, penta 5, hexa 6, and so on. The naming format is prefix plus name of first element, plus prefix plus base name of second element, plus ide ending. A key rule is that the prefix mono is usually omitted for the first element in the name. If there's only one atom of the second element, you do use mono. Your example PO is named diphosphorus pentoxide. CS would be carbon disulfide, mono omitted for carbon.
Acids have their own special naming rules, too, based on their formulas.
They do. There are two main categories mentioned. Binary acids contain hydrogen and just one other nonmetal element. Their names start with the prefix hydro, followed by the base name of the nonmetal, with the ending changed to iic acid. So HCl is hydrochloric acid, HF is hydrofluoric acid.
And the other type, oxyacids.
Oxyacids contain hydrogen, oxygen, and another nonmetal element. They contain an oxyanion. Their names are derived from the name of the oxyanion they contain. If the oxyanion name ends in acast, the corresponding acid name ends in oxyacid. For example, H-arrow contains the phosphate ion. It's called the phosphoric acid. If the oxyanion name ends in oxide, the acid name ends in oxyacid. For example, HASO contains the sulfide ion, so it's called sulfurous acid. No hydro prefix for oxyacids.
Gotcha. All these rules help us name the compounds, but going back to structure, Lewis structures actually show us how the valence electrons are arranged when the atoms bond.
Yes, exactly. Lewis structures, or Lewis dot diagrams, are visual representations. They use dots around the element symbol to show the valence electrons of an atom. When atoms form molecules or polyatomic ions, the Lewis structure shows how these electrons are shared as lines representing covalent bonds, one line per shared pair, or held as lone pairs, dots not involved in bonding, around each atom. Their main purpose is to illustrate how the atoms achieve a stable electron configuration, usually satisfying the octet rule, or duet rule for hydrogen. Being able to draw the Lewis structure for an element like phosphorus, showing its 5 valence electrons, is the first step towards drawing the structure for a compound containing phosphorus.
Okay, so we know about atoms, bonds, shapes, naming. Now, what happens when these compounds actually interact and change? That's chemical reactions, right? Why are they so important?
Chemical reactions are, well, the heart of chemistry. They're how substances transform into new substances. Your sources highlight just how ubiquitous and important they are, from, those fun grade school volcanoes, to the combustion reactions that power our cars, to precipitation reactions used in things like water treatment or even laundry detergents, and even the neutralization reactions happening in your own body when saliva buffers acids or you take an antacid for heartburn. Reactions fundamentally involve the rearrangement of atoms.
And we represent these rearrangements using chemical equations.
Right. An equation shows the starting materials, the reactants on the left side, and the substances formed, the products, on the right side, separated by an arrow indicating the transformation. The absolutely critical principle when writing and using chemical equations is the law of conservation of mass.
Meaning atoms aren't created or destroyed in a normal chemical reaction.
Exactly. You must have the same number of atoms of each element on the reactant side as you have on the product side. This is achieved by balancing the equation.
And the key to balancing is that you can only change the coefficients, the big numbers, in front of the chemical formulas. You never change the subscripts within the formulas.
That is the absolute golden rule. Changing a subscript changes the identity of the substance itself. Balancing involves adjusting the coefficients until the atom counts match on both sides. Your sources outline a general procedure. Write the unbalanced skeletal equation first. Then balance atoms one element at a time by changing coefficients. Often good to start with elements appearing in only one compound on each side, maybe metals first, then polyatomic ions if they stay intact, then other nonmetals, then hydrogen, then oxygen last is often helpful. If you end up with fractional coefficients, multiply the whole equation by a number to clear them. Finally, always double-check that all atom counts are equal on both sides. Your materials provide many examples to practice balancing different types of reactions.
Speaking of types, your materials also categorize reactions into several common patterns.
Yes, recognizing these patterns can help predict products or understand what's happening. The main types mentioned are synthesis, where two or more simpler substances combine to form a more complex one, A plus B, APB. Decomposition, the opposite, where a complex substance breaks down into simpler ones, AB, A plus B. Single displacement, or single replacement, where one element kicks out another element from a compound, A plus BC, AC plus B. Whether this happens often depends on the relative reactivity of the elements, which relates to the activity series we'll mention with redox. And double displacement, or double replacement, where two compounds essentially swap partners, AB plus CD, AD plus CB.
Precipitation reactions are a type of double displacement.
Often, yes. A precipitation reaction is one where two soluble ionic compounds react in solution to form an insoluble ionic compound, the precipitate which falls out of solution as a solid. To predict if a precipitate will form, you look at the potential products from the partner swap and check solubility rules, which your sources likely provide or assume you have access to see if either potential product is insoluble in water.
Combustion reactions seem like another really common type.
Very common. Combustion is basically rapid reaction with oxygen, usually producing heat and light burning. A key type to know is the combustion of hydrocarbons, compounds containing C and H, maybe O. When these burn completely in sufficient oxygen, the products are always carbon dioxide, CH2Os, and water, HO. Your sources give examples like burning methane, CH, octane, CROs and gasoline, or ethanol, CROs.
And neutralization reactions.
These are the reactions between an acid and a base. The typical products are a salt, an ionic compound, and water. Those examples of stomach acid, HCl, being neutralized by antacids like calcium carbonate or magnesium hydroxide, MgOH, are perfect examples of neutralization in action.
The sources also give specific attention to another broad category, redox reactions. What defines those?
Redox stands for reduction oxidation. These are reactions characterized by the transfer of electrons from one reactant to another. You can often spot them if a substance reacts with elemental oxygen, or if a metal reacts with a non-metal, or more generally, anytime the oxidation states, a sort of charge accounting system for atoms and compounds, of elements change during the reaction.
And the key terms are oxidation and reduction. Oxidation is loss, reduction is gain of electrons. Oil rig.
That's the classic mnemonic, yeah. Oxidation is the process of losing electrons. The substance that loses electrons is said to be oxidized. Reduction is the process of gaining electrons. The substance that gains electrons is said to be reduced. They always happen together in a redox reaction. If something loses electrons, something else must gain them.
And there are oxidizing and reducing agents.
Right. The substance that causes oxidation by taking electrons away is itself reduced, so it's called the oxidizing agent. The substance that causes reduction by giving electrons away is itself oxidized, so it's called the reducing agent. Simple examples in your sources like nitrogen reacting with oxygen, NuRO plus ORO at 2NO, or carbon monoxide reacting with oxygen, 2CO plus ORO 2CO, illustrate these electron transfers, though tracking oxidation states might be needed to see it clearly.
Can we predict if a redox reaction, like a single displacement reaction, will happen spontaneously?
Yes, often we can use the activity series. This series ranks metals, and sometimes hydrogen, based on how easily they are oxidized, lose electrons. A metal higher up on the activity series is more reactive and will spontaneously displace the ions of a metal lower down on the series from a solution. Your sources shows this with iron, F reacting with lead ions. PB time is higher, so it displaces lead. But iron does not react with magnesium ions, MjKO, because magnesium is higher than iron on the series.
And this electron transfer in spontaneous redox reactions can actually be harnessed.
Absolutely.
Yeah.
That's the basis of electrochemical cells, like batteries, which are technically voltaic or galvanic cells. These devices are designed to separate the oxidation and reduction half reactions physically, but connect them with a wire, forcing the transferred electrons to slow through the external circuit, generating usable electrical current. The source mentions the anode, where oxidation occurs, and cathode, where reduction occurs.
Okay, so reactions rearrange atoms. But how do we actually count or quantify the huge numbers of atoms and molecules involved in these reactions? They're incredibly tiny.
That's where the absolute genius of the mole concept comes in. Chemists needed a convenient way to count unimaginably large numbers of particles, so they defined the mole. One mole is simply a specific number of particles, Avogadro's number, which is 6.022 by 10^5 miles. Whether it's atoms, molecules, ions, electrons, a mole is always that number of them. It's the standard unit chemists use for the amount of substance.
And your sources give those really vivid examples to try and help us wrap our heads around just how colossal that number is.
They do. A mole of copper pennies would cover the entire Earth's surface many meters deep. A mole of sugar crystals would cover the state of Texas several centimeters deep. It's meant to impress upon you that even a small, weighable amount of substance contains an enormous number of particles, and the mole lets us handle that.
And the mole is directly linked to mass through the molar mass.
Exactly. The molar mass of a substance is defined as the mass, in grams, of exactly 1 mole of that substance. Its units are grams per mole. Wrong. How do you find it? You simply add the atomic masses from the periodic table of all the atoms present in the chemical formula of the substance. Your source shows the calculation for CCl euros, for instance. Molar mass is the key bridge between the mass of a sample, something we can easily measure in the lab, and the number of moles it contains.
And the mole acts like a central hub, or like the center of a map, connecting mass, the number of particles, and even volume for gases under certain conditions.
Precisely. That's often called the mole map. The mole is the central unit. You can convert between the mass of a substance, in grams, and the number of moles using the molar mass as your conversion factor. You can convert between the number of moles and the actual number of particles, atoms, molecules, formula units, using Avogadro's number as the conversion factor. And specifically for gases at standard temperature and pressure, STP, which is 0 degrees C and 1 atm pressure, there's another useful conversion. 1 mole of any ideal gas occupies a volume of 22.4 liters. So molar volume, 22.4 liter, connects moles and volume for gases at SPP. Your sources demonstrate all these crucial conversions with plenty of examples: grams of moles, moles back to grams, moles to atoms or molecules, atoms, molecules back to moles, moles of gas to liters at STP, liters back to moles. And often you need multiple steps, always going through the mole as the central connection.
Can the chemical formula itself be used as a mole-based conversion factor?
Yes, absolutely. The subscripts in a chemical formula don't just tell you the ratio of atoms in one molecule. They also tell you the ratio of moles of atoms within 1 mole of the compound. For example, in cocoas, the formula tells us that 1 mole of calcium carbonate contains 1 mole of calcium atoms, 1 mole of carbon atoms, and 3 moles of oxygen atoms. This mole ratio, derived directly from the subscripts, acts as a conversion factor between moles of the compound and moles of a specific element within that compound. Your source uses this to calculate moles of oxygen in moles of cacao.
And mass percent composition can also be used in conversions involving mass.
Right. If you know the mass percentage of an element in a compound, say your source mentions titanium is 59.9% by mass in titanium oxide, that percentage literally means 59.9 grams of titanium per 100 grams of titanium oxide. This relationship gives you a direct conversion factor between the mass of the compound and the mass of that specific element within it.
Okay, all these conversion grams, moles, particles, liters seem absolutely essential for stoichiometry. That's the calculations based on balanced chemical equations, right?
Exactly. Stoichiometry is the quantitative study of reactants and products in chemical reactions. The coefficients in a balanced chemical equation are the key. They represent the mole ratios in which substances react and are formed. That equation for making water, 2H0 plus O0, 2H0, doesn't just say 2 hydrogen molecules react with 1 oxygen molecule. It fundamentally tells us that 2 moles of H0 react with 1 mole O0 to produce 2 moles of HO. These coefficients give us the mole-to-mole conversion factors between any two substances in the reaction.
And we use these mole ratios from the balanced equation to calculate things like how much product can I make from a certain amount of reactant, or how much reactant do I need to make a certain amount of product.
That is the absolute core of stoichiometry calculations. The general pathway is often 1. Start with the given amount of one substance, usually mass in grams, but could be volume of gas at STP or number of particles. 2. Convert that given amount into moles using the appropriate conversion factor, molar mass, molar volume, or Avogadro's number. 3. Use the mole ratio derived from the coefficients in the balanced chemical equation to convert moles of the given substance into moles of the substance you want to find, the target substance. 4. Convert the moles of the target substance into the desired units, grams using its molar mass, liters of gas at STP, etc. Your sources provide numerous examples walking through these steps, calculating moles of product from moles of reactant, grams of reactant to grams of product, grams of reactant to liters of gas product, and so on. Mastering this gram, mole, gram pathway, or variations, is critical.
Stoichiometry can also involve solutions using molarity, right?
Yes. If a reaction happens in solution, amounts are often measured by volume, and concentration is given in molarity. Remember, molarity M is moles of solute per liter of solution, mole. Molarity acts as a direct conversion factor between the volume of a solution, in liters, and the number of moles of solute contained in that volume. The neutralization example in your sources demonstrates this beautifully. Calculating the volume of a sodium hydroxide, NaOH, solution needed to completely react with a given volume and molarity of sulfuric acid HCO as solution. You use the acid's molarity and volume to find moles of acid, then the mole ratio from the balanced neutralization equation, acid plus base, salt plus water, to find moles of base needed, and finally use the base's molarity to calculate the required volume of the base solution.
Your sources also briefly mention concepts like limiting reactant, theoretical yield, and percent yield in the context of stoichiometry.
Right. In many real reactions, you don't mix reactants in the exact stoichiometric ratio given by the balanced equation. Usually, one reactant will get completely used up before the others. That one is called the limiting reactant, or limiting reagent. It's limiting because it determines the maximum amount of product that can possibly be formed.
So the reaction stops when the limiting reactant runs out.
Exactly. The maximum amount of product you could theoretically make, assuming the limiting reactant reacts completely according to the balanced equation, is called the theoretical yield. It's a calculated amount based on stoichiometry. The actual amount of product you obtain when you perform the reaction in the lab is called the actual yield. The percent yield is then just a measure of efficiency, actual yield, theoretical yield, by 100%. Your sources mention a common way to identify the limiting reactant. Calculate the theoretical yield of product based on the starting amount of each reactant separately. Whichever reactant produces the smaller amount of product is the limiting reactant, and that smaller amount is the theoretical yield.
Okay, let's shift gears slightly but stay related. We were just talking about molarity and reactions in solution. Let's dive a bit more into mixtures, specifically solutions.
Sounds good. So a solution, as we defined earlier, is a homogeneous mixture. It looks uniform throughout. You can't see separate parts. It's made up of at least two components. The solvent, which is the substance that does the dissolving and is typically present in the larger amount, and the solute, which is the substance being dissolved, and it's typically present in the smaller amount.
And solutions aren't always just a solid dissolved in a liquid, like salt water.
No, definitely not. While that's a very common type, solid solute and liquid solvent, you can have many other types. Gas dissolved in liquid, like carbon dioxide and soda. Liquid dissolved in liquid, like ethanol and water, making vodka, or acetic acid and water, making vinegar. Gas dissolved in gas, like air itself, which is mostly nitrogen solvent with oxygen and other gas solutes. Or even solid dissolved in solid, like metal alloys brass is zinc dissolved in copper.
Concentration is the term we use to describe how much solute is actually in the solution, right?
Exactly. Concentration quantifies the amount of solute present in a given amount of solvent, or a given amount of the total solution. There are several ways to express concentration mentioned in your materials. We already discussed molarity M, which is moles of solute per liter of solution.
What about molality? That sounds similar but different.
It is slightly different, and the difference is important in some contexts, especially when temperature changes are involved. Molality, usually symbolized with a lowercase m, is defined as moles of solute per kilogram of solvent. Notice it's per kilogram of solvent, not per liter of solution like molarity. Mass percent composition is another way. It's the mass of the solute divided by the total mass of the solution multiplied by 100%. It tells you grams of solute per 100 grams of solution.
And your sources show how to calculate these concentration units.
Yes, there are examples. For molarity, it's moles divided by volume in liters, like your sodium fluoride example. For molality, it's moles of solute divided by mass of solvent in kilograms, examples with sucrose or ethylene glycol. Your sources also cover dilution calculations, which is how you make a less concentrated solution from a more concentrated one by adding more solvent. The key equation there is MOV, where MO euro are the initial molarity and volume, and MO euro and V are the final molarity and volume after dilution. And remember being able to calculate the concentration of individual ions when an ionic compound dissolves. If you have a 1M solution of NaCl, it's 1M in Na ions and 1M in clay ions. But if you have 1M MuL, it's 1M in Cl ions, but 2M in clay ions, because each formula unit gives 2 chloride ions. You need to use the formula subscripts.
Related to solutions is solubility. That's about how much solute can dissolve, right?
Precisely. Solubility is typically defined as the maximum amount of solute that can dissolve in a specific amount of solvent at a given temperature to form a saturated solution. If you try to add more solute than the solubility limit, it just won't dissolve.
And temperature affects solubility. Does it always make things more soluble if you heat them up?
Not always. It depends on the state of the solute and solvent. For most solid solutes dissolving in liquid solvents, solubility increases as temperature increases. Think dissolving more sugar in hot tea than in iced tea. Same for most liquid solutes and liquid solvents. However, for gases dissolving liquids, the opposite is generally true. Solubility of gases decreases as temperature increases. That's why a warm soda goes flat faster than a cold one. The TO gas is less soluble at higher temperatures and it skids more easily.
And when things dissolve, particularly in water, the type of particle that actually ends up floating around affects the solution's properties, like electrical conductivity.
Big time. This relates back to ionic versus molecular compounds. If the solute is an ionic compound, like salt, NaCl, when it dissolves in water, it dissociates into its constituent ions, NaOH and KeLa. These mobile charged ions allow the solution to conduct electricity. We call such solutes strong electrolytes, and the solution is an electrolyte solution.
Uh-huh.
But if the solute is a molecular compound that doesn't ionize in water, like sugar, CHRO, it dissolves as intact neutral molecules. Since there are no free-moving charges, these solutions do not conduct electricity well or at all. We call these solutes non-electrolytes, and the solution is a non-electrolyte solution. There are also weak electrolytes, like weak acids that only partially ionize, so they conduct electricity poorly.
Okay, we've touched on acids, bases, and redox reactions several times as examples, but your sources give them their own dedicated look as special reaction types.
Right, there are fundamental categories. For acids and bases, the common definition used is the Brønsted-Lowry definition. It's elegantly simple. An acid is a proton H donor, and a base is a proton acceptor.
So it's all about the proton transfer.
Exactly. Your examples show this. When HCl dissolves in water, the HCl molecule donates its proton to a water molecule, forming hydronium ion and chloride ion, so HCl acts as the acid. When ammonia dissolves in water, it actually accepts a proton from a water molecule, forming ammonium ion, NH0, and hydroxide ion. So NH0 acts as the base in this case, and water acts as the acid.
And acids and bases aren't all the same strength. They're strong versus weak.
Correct. The strength refers to the extent to which they ionize or react with water. Strong acids, like HCl, H0, HNO, ionize completely in water. Essentially, every molecule donates its proton. Strong bases, like NaOH, KOH, metal hydroxides from group 1 and 2, dissociate completely in water to produce hydroxide ions. Weak acids and weak bases, on the other hand, only ionize or react partially with water. Your source uses HF, hydrofluoric acid, as an example of a weak acid. Only a small fraction of the HF molecules actually donate their proton to water at any given time. Most remain as intact HF molecules. This equilibrium between ionized and unionized forms is key for weak acid bases.
And this difference in ionization directly relates to whether they are strong or weak electrolytes.
Precisely. Because strong acids and strong bases produce a high concentration of ions in solution, they're strong electrolytes. Their solutions conduct electricity well. Weak acids and weak bases produce only a low concentration of ions, so they're weak electrolytes. Their solutions conduct electricity poorly. Non-electrolytes, remember, don't produce ions and don't conduct.
And the classic reaction between an acid and a base is neutralization.
Yep, acid plus base typically yields a salt, an ionic compound made from the cation of the base and the anion of the acid, plus water. We keep coming back to those stomach acid, HCl neutralization examples with antacids like calcium carbonate or magnesium hydroxide, MgOH. They perfectly illustrate this reaction type, removing excess acid.
Okay, to actually measure how acidic or basic a solution is, we use the pH scale.
Right. The pH scale is a logarithmic scale used to conveniently express the concentration of hydronium ions in an aqueous solution. A low pH less than 7 means the solution is acidic. A high pH greater than 7 means the solution is basic. A pH of exactly 7 at 25 degrees C means the solution is neutral. The pOH scale is similar but based on the hydroxide ion concentration.
And pH and pOH are related.
Yes, they are linked through the autosynchronization of water. At 25 degrees C, pH plus pOH always equals 14. Also, the product of the hydronium and hydroxide concentrations, HOH, equals a constant called Kw, which is 1.0 by 10 euro at 25 degrees C. Your sources show the key calculations. Finding pH from HO, finding HO from pH, and relating HO and OH, these calculations allow you to classify any aqueous solution as acidic, basic, or neutral based on its pH or ion concentrations.
Okay, and just to quickly circle back one more time to redox reactions.
Electron transfer, that's the defining feature. Remember oil reg. Oxidation is loss of electrons. Reduction is gain of electrons. The substance oxidized is the reducing agent. The substance reduced is the oxidizing agent. The activity series helps predict if single displacement redox reactions will be spontaneous. And voltaic galvanic cells, like batteries, are practical devices that harness the energy released from spontaneous redox reactions to generate electricity.
Now, for something that sounds a bit paradoxical perhaps, dynamic chemistry and equilibrium. It feels like equilibrium means things stop, but you're saying it's dynamic.
That is absolutely the key insight. Chemical equilibrium is not a static state where reactions stop. It's a highly dynamic state. It's reached when the rate at which reactants are forming products, the forward reaction rate, becomes exactly equal to the rate at which products are turning back into reactants, the reverse reaction rate.
So reactions are still happening, just balanced.
Precisely. On the macroscopic level, what we can see or measure the concentrations of reactants in products appear to remain constant. It looks like nothing is changing. But at the molecular level, both the forward and reverse reactions are continuously occurring at the same speed. Your sources make a really interesting point connecting this to life. Living organisms maintain a state of controlled disequilibrium with their environment. Reaching true equilibrium for a living system essentially means death.
How do we quantify where the equilibrium lies? Does it favor products or reactants?
We use the equilibrium constant, Keck, or sometimes just K or K to C if concentrations are used. Keck is a value calculated from the ratio of product concentrations to reactant concentrations at equilibrium. A large value of Keck, much greater than 1, means that at equilibrium the mixture contains mostly products, the equilibrium lies to the right. A small value of Keck, much less than 1, means the mixture contains mostly reactants. The equilibrium lies to the left. A Keck value near 1 means there are significant amounts of both reactants and products at equilibrium.
And how do we write the expression to calculate Keck?
The expression is set up based on the balanced chemical equation for the reversible reaction. It's the mathematical product of the equilibrium concentrations of the chemical products, each raised to the power of its stoichiometric coefficient, divided by the mathematical product of the equilibrium concentrations of reactants, each raised to the power of its coefficient. A critical rule applies to heterogeneous equilibria, reactions involving substances in different phases. The concentrations of pure solids and pure liquids are considered constant and are therefore omitted from the Keck expression. Only gases, often expressed as partial pressures, kT, and dissolved species, concentrations in mol, Kc, appear in the expression. Your sources show examples for gas phase reactions, like H euros plus I euros to HI, decomposition of a solid producing a gas like KClOs, KClS, plus K euro, where K only depends on O, and the dissolution of sparingly soluble ionic solids.
That last one, dissolving solids, relates to KCC.
Yes, the solubility product constant, KSP, is just a specific type of equilibrium constant, KAC, that applies to the dissolution of ionic compounds that are only slightly soluble in water. For example, for BSO, Bakueshui, the KSP expression is just Bakuoso, the solid BSO is emitted. Your sources give several examples like AGI, KJOH, HO, MNOH, ESO. Case p-values tell us how soluble a compound is smaller. KSP means less soluble. You can relate KSP to the molar solubility, the moles of compound that dissolve per liter of saturated solution, as shown in your HCl example.
And you can calculate the value of KEK if you measure the concentrations once the reaction reaches equilibrium.
Absolutely. If you experimentally determine the concentrations of all the species that appear in the KEK expression, once the system is settled into equilibrium, you just plug those concentration values into the KEK expression you wrote and calculate the numerical value of KEK, like in your H plus I or CO plus HU examples.
What happens if you have a system that is at equilibrium and then you poke it, you disturb it somehow?
That's where Le Chatelier's principle comes in. It's a fundamental concept for understanding equilibrium. It states that if a change of condition, a stress, is applied to a system already at equilibrium, the system will shift its equilibrium position in a direction that tends to relieve or counteract that stress in order to reestablish equilibrium.
Okay, so what kind of stresses are we talking about, like changing concentrations?
Yes. If you add more of a reactant to a system at equilibrium, the stress is the increased reactant concentration. The system relieves this by shifting to the right, consuming some of the added reactant and forming more products. Conversely, if you add more product, the system shifts left, consuming product and forming more reactants. If you remove a substance, the equilibrium shifts in the direction that replaces what you removed.
What about changing the volume or pressure, especially if gases are involved?
This applies mainly to reactions involving gases, where the total number of moles of gas changes between reactants and products. If you decrease the volume of the container, which increases the total pressure, the stress is the increased pressure. The system relieves this by shifting in the direction that produces fewer moles of gas particles, as fewer moles exert less pressure. If you increase the volume, decreasing pressure, the system shifts towards the side with more moles of gas particles. Your KClU's decomposition example, solid plus gas, illustrates this well. Decreasing volume shifts left towards fewer gas moles, increasing volume shifts right towards more gas moles. If a reaction had equal moles of gas on both sides, changing volume pressure has no effect on the equilibrium position.
And temperature. How does changing temperature affect equilibrium?
Temperature changes affect equilibrium differently than concentration or pressure changes, because changing temperature actually changes the value of the equilibrium constant, KEK, itself. The direction of the shift depends on whether the reaction is exothermic, releases heat, EKH is negative, or endothermic, absorbs heat, EKH is positive. Think of heat as a product in an exothermic reaction, reactants, products plus heat, and as a reactant in an endothermic reaction, reactants plus heat products.
Okay.
So if you increase the temperature, add heat of an exothermic reaction, you're adding a product. Le Chatelier says the system shifts left to consume that added heat. KEK decreases. If you cool it down, remove heat, it shifts right to produce more heat. KEK increases. For an endothermic reaction, increasing temperature, adding a reactant, shifts it right, consuming heat. KEK increases. Cooling it shifts it left. KEK decreases.
This connects directly to energy changes in reactions, which your sources touch on with some thermodynamics basics.
Right. We often classify reactions based on their heat flow. Exothermic reactions are those that release heat energy into the surroundings. Combustion is a classic example. It feels hot. Endothermic reactions absorb heat energy from the surroundings. Melting ice or vaporizing water requires energy input, so they're endothermic processes. They feel cold if they draw heat from you.
And enthalpy of reaction, Arch Eric's saying, quantifies this heat flow.
Yes, enthalpy H is a thermodynamic property related to the total heat content of a system. The change in enthalpy during a reaction, Arch Eric's N, often just written H, represents the amount of heat absorbed or released by the reaction when it occurs at constant pressure. By convention, H is negative for an exothermic reaction.
Yeah.
Heat released, system loses enthalpy. And positive for an endothermic reaction, Heat absorbed, system gains enthalpy.
And the value of xi correlates the amount of reaction to the amount of energy.
Exactly. It's usually given in units like kilojoules per mole, kJ-mole, of reaction as written in the balanced equation. Your propane combustion example, CH plus 5 Oreos plus 4 euro, shows that 1 mole of propane reacting releases 2044 kilojoules of heat, so CaH ordinance 2044 kilojoules. This HH value acts as a stoichiometric conversion factor, relating moles of reactant product to the amount of heat exchanged.
And what about calculating heat exchange when something just changes temperature without a reaction?
Your sources include the important formula for calculating heat transfer, Q, associated with the temperature change. Q equals mc at T. Here, Q is the amount of heat absorbed or released, M is the mass of the substance, C is the specific heat capacity of the substance, a property that tells how much heat is needed to raise the temperature of 1 gram by 1 degree Celsius or 1 Kelvin, and AT is the change in temperature, T final to initial. This lets you calculate, for instance, how much heat is needed to warm up a sample of water, or how much heat is released when a piece of hot metal cools down, as shown in your water and lead examples.
Okay, shifting from chemical transformations in energy to transformations within the atom's core itself, nuclear chemistry.
Right. This branch deals specifically with changes occurring within the atomic nucleus.
Yeah.
Radioactivity is a key phenomenon here. It's the spontaneous process by which unstable atomic nuclei decay, or breakdown, by emitting particles or electromagnetic radiation energy.
And a really central concept in radioactivity is half-life. What is that exactly?
The half-life of a radioactive isotope is the time it takes for exactly half of the radioactive nuclei in any given sample of that isotope to undergo decay. It's a characteristic constant for each specific radioactive isotope. Some have half-lives of fractions of a second, others billions of years.
So it's a predictable rate of decay.
Very predictable, statistically. After one half-life passes, 50% of the original sample remains undecayed. After 2 half-lives pass, total time equals 2x zeros. Half of that remaining amount decays, leaving 25% of the original. After 3 half-lives, 12.5% remains, half of 25%, and so on. Your thorium-232 graph concept visually illustrates this exponential decay pattern. Your sources provide calculation examples using half-life, like figuring out how long it takes for a sample of uranium-235 to decay to 1/8 of its initial amount, that would be 3 half-lives, or how much technetium-99 meter remains after a certain time.
And when these unstable nuclei decay, they can emit different kinds of particles or radiation.
Yes, there are several common types of radioactive decay. We can represent these nuclear transformations using nuclear equations, which are similar to chemical equations but track the mass numbers, A superscript, and atomic numbers, Z subscript, of the nuclei involved. Crucially, both the total mass number and the total atomic number must be conserved. They must balance on both sides of the equation.
What are some common decay types mentioned?
Alpha decay is one. This involves the emission of an alpha particle, which is essentially a helium nucleus, consisting of 2 protons and 2 neutrons. Its symbol is OAhe or OYE. When a nucleus undergoes alpha decay, its mass number decreases by 4 and its atomic number decreases by 2. Your source shows the nuclear equation for the alpha decay of polonium-214 Oures.
Okay, alpha decay changes both A and Z. What about positron emission?
Positron emission is another type. A positron is like an electron, but it has a positive charge, +1 instead of negative. Its symbol is AUROO or ball. Positron emission typically happens in proton-rich nuclei, where a proton inside the nucleus effectively transforms into a neutron and a positron is ejected from the nucleus to conserve charge. So in positron emission, the mass number A remains unchanged. Proton becomes neutron, so total count is same, but the atomic number Z decreases by 1 less proton. Your sources provide several examples of writing nuclear equations for positron emission involving isotopes like Bi-206, Mg23, Ge68, Co55, Na22, and F18. Beta decay, emission of an electron at rest, is also common and increases Z by 1, but maybe focus on the ones with examples.
Beyond radioactive decay, there are also nuclear reactions where nuclei are deliberately split or combined, like nuclear fission.
Exactly. Nuclear fission is the process where a heavy atomic nucleus, like uranium-235 or plutonium-239, is split into 2 or more smaller, lighter nuclei, typically by bombarding it with a neutron. This splitting releases a tremendous amount of energy, much more than chemical reactions, and also releases additional neutrons.
And those released neutrons can cause more fission, a chain reaction.
Precisely. If the neutrons released by one fission event go on to strike other nearby fissionable nuclei, causing them to split and release even more neutrons, you can get a self-sustaining chain reaction. If enough fissionable material is packed together what's called a critical mass, this chain reaction can occur very rapidly, which is the basis of atomic bombs.
But fission can also be controlled for energy production.
Yes, that's how nuclear power plants work. In a nuclear reactor, the fission chain reaction is controlled, usually using control rods made of materials that absorb neutrons, like cadmium or boron. By adjusting how far these rods are inserted into the reactor core, operators can control the rate of fission, keeping it sustained but preventing it from escalating out of control. The immense heat generated by the controlled fission is used to boil water, producing high-pressure steam.
Which then turns turbines to generate electricity, just like in a conventional power plant.
Exactly. The nuclear reaction is just the heat source.
What about nuclear fusion? That's the opposite, right? Combining light nuclei.
Right. Nuclear fusion is the process where very light atomic nuclei, like isotopes of hydrogen, deuterium and tritium, combine or fuse together to form a heavier nucleus, like helium. This process releases even more energy per unit mass than fission.
And this is what powers stars.
Yes, nuclear fusion is the fundamental energy source of our sun and all other stars. Inside their incredibly hot and dense cores, hydrogen nuclei are constantly fusing together to form helium, releasing the vast amounts of energy that make them shine. Harnessing fusion controllably on Earth for power generation is a major scientific goal, but it's extremely challenging because of the incredibly high temperatures and pressures required.
And these nuclear processes and radioactive isotopes, they have practical applications beyond bombs and power plants.
Oh, absolutely. Radioactive isotopes, because their decay is predictable and they emit detectable radiation, have numerous uses. In medicine, they're used as tracers for diagnostic imaging, isotope scanning. The isotope is incorporated into a compound that targets a specific organ or tissue, and its emitted radiation is detected to create an image. Radiation therapy uses high-energy radiation to target and destroy cancer cells.
And radioactive dating, like carbon-14 dating.
That's a classic application. Carbon-14 is a radioactive isotope of carbon that's naturally present in the atmosphere and incorporated into all living organisms. When an organism dies, it stops taking in new C14. The C14 already present then decays the known half-life, about 5,730 years. By measuring the amount of C14 remaining in an ancient organic sample like wood, bone, or cloth, and comparing it to the amount expected in living tissue, scientists can estimate how long ago the organism died. Your sources also mention radon gas, a naturally occurring radioactive gas that comes from the decay of uranium in rocks and soil. It can seep into buildings and accumulate, and because it's inhaled, it's a significant contributor to background radiation exposure and a known risk factor for lung cancer.
Wow, okay. From the nucleus, let's zoom back out and finish with the chemistry of one particular element that's absolutely central to life. Carbon, organic chemistry, and biochemistry.
Right. Organic chemistry is formally defined as the study of carbon-containing compounds. Carbon is unique in its ability to form 4 stable covalent bonds, and crucially to bond extensively with itself, forming long chains, branched chains, and complex ring structures. This ability allows for an almost infinite variety of organic molecules, which form the structural basis and carry out the functions of all living organisms.
The simplest organic compounds are the hydrocarbons, just carbon and hydrogen.
Yep, and they are categorized based on the types of carbon-carbon bonds they contain. Alkenes contain only single bonds between carbon atoms. They are called saturated hydrocarbons because they have the maximum possible number of hydrogen atoms bonded to the carbon chain. Alkenes contain at least one carbon-carbon double bond, and alkenes contain at least one carbon-carbon triple bond. Because of the multiple bonds, alkenes and alkenes have fewer hydrogen atoms than the corresponding alkene with the same number of carbons, so they're called unsaturated hydrocarbons. Your sources mention the general formulas. Alkenes...
Whole system for naming these organic compounds too, which can get quite complex.
It can, but there's a systematic approach based on IUPAC rules. For simple alkanes, the name is based on the number of carbons in the longest continuous chain. Methane 1, ethane 2, propane 3, butane 4, pentane 5, hexane 6, etc. Any branches attached to the main chain are named as substituents, like methyl for Marchiers, ethyl for Maris Euros, and their position on the main chain is indicated by a number. Your sources show an example like 3-pal-3-dimethylpentane, illustrating how to find the longest chain, number it to give substituents the lowest possible numbers, and assemble the name.
And naming alkenes and alkenes is similar, but includes the position of the multiple bond.
Yes, the name needs to indicate where the double bond for ane ending, or triple bond for ane ending, starts along the main chain, using the lowest possible number. Substituents are named and numbered as well. Your source problems give examples like 1-pentene, double bond starts at C1 of a 5-carbon chain, 3-octene, Triple bond starts at C3 of an 8-carbon chain, and more complex ones with both multiple bonds and substituents like 4-ethyl, 3-methyl-2-octene.
But organic chemistry isn't just about hydrocarbons. Many organic molecules have other atoms or groups of atoms attached, called functional groups.
Exactly. Functional groups are specific arrangements of atoms bonded to the carbon skeleton of an organic molecule. They are important because they are the sites where most chemical reactions occur, and they largely determine the molecule's chemical properties and classification. Your sources list several key functional groups you should probably recognize. Alcohols contain an OH group, ethers, O-linking 2 carbons, aldehydes and ketones, both contain a CO carbonyl group, differs by location, carboxylic acids, a HeOH group, esters, COO group, and amines contain nitrogen, like NACH and HA. Each group imparts characteristic properties.
And we encounter molecules with these functional groups constantly in everyday life.
All the time. Lactic acid, a carboxylic acid, found in sour milk and produced in muscles during exercise. Citric acid, another carboxylic acid, responsible for the sour taste of citrus fruits. Esters are often responsible for pleasant fruity or floral smells and flavors. Your examples mention ethyl butanoate, pineapple smell, and methyl butanoate, apple smell. And polymers, which we mentioned before, are huge molecules made by linking together many small organic units. Monomers, things like polyethylene in plastic bags and bottles, nylon in clothing and fishing line, and PVC, polyvinyl chloride used for pipes, are all synthetic organic polymers based on repeating functionalized units.
And organic chemistry naturally leads into biochemistry, the chemistry of life itself.
Yes, biochemistry applies the principles of chemistry, especially organic chemistry, to understand the molecules and processes occurring within living organisms. It focuses on the structure and function of large biological macromolecules. Your sources highlight the 4 major classes: carbohydrates, lipids, proteins, and nucleic acids.
Carbohydrates are sugars and starches.
Right. They primarily function as energy sources and structural components. They range from simple sugars called monosaccharides like glucose to disaccharides, to monosaccharides linked like sucrose or table sugar, to complex carbohydrates called polysaccharides, long chains of monosaccharides like starch for energy storage or cellulose for structure. Your sources distinguish these based on sketch examples.
Lipids are the fats, oils, waxes, things that don't dissolve in water.
Exactly. They are defined by their insolubility in water. They are nonpolar. Lipids serve many roles: long-term energy storage, insulation, formation of cell membranes, and as hormones, like steroids. Key types mentioned include fatty acids, triglycerides. Fats and oils differ based on saturated versus unsaturated fatty acids, implied by structure sketches. Phospholipids, major component of cell membranes, structurally distinct from triglycerides as noted. And steroids have a characteristic 4-ring structure.
Proteins seem incredibly complex and versatile. They're polymers of amino acids.
Yes. Proteins are polymers, made from 20 different types of amino acids linked together in long chains by peptide bonds. The specific sequence of these amino acids, the primary structure, determines how the protein chain folds up into a complex 3-dimensional shape. This 3D structure includes secondary structures, like alpha helices and beta sheets, regular folding patterns, tertiary structure, the overall 3D folding of a single polypeptide chain, and sometimes quaternary structure, when multiple polypeptide chains assemble together. A protein's intricate shape is absolutely critical for its specific function, whether it's acting as an enzyme, transporting molecules, providing structure, like keratin in hair and nails, mentioned as an example, or signaling.
And finally, nucleic acids, DNA and RNA, the molecules of heredity.
Right. Deoxyribonucleic acid, DNA, and ribonucleic acid, RNA, are polymers made of repeating units called nucleotides. Their primary function is to store and transmit genetic information. DNA contains the genetic blueprint for building and operating an organism. RNA plays various roles in reading that blueprint and synthesizing proteins. Your sources mention the 4 main nitrogenous bases found in DNA nucleotides: adenine A, cytosine C, guanine G, and thymine T, and that the specific sequence of these bases along the DNA chain forms the genetic code. This code is read in 3 base units called codons, each specifying a particular amino acid to be added during protein synthesis. Wow. Okay, we have genuinely covered a huge amount of ground there, haven't we? From the tiniest subatomic particles and the fundamental forces and rules governing them, all the way through how those particles combine, rearrange in reactions, how we measure and count them using things like the mole, how energy flows through these chemical processes, and even how these same basic principles apply in the, mind-boggling complexity of living systems and inside the atomic nucleus itself.
Yeah, our goal here was really to take that stack of sources you provided, all those notes and articles, and try to pull out those essential nuggets, the key definitions you need to know, the rules for naming and calculating, the trends, the important examples, and hopefully show how they all interconnect.
Think of it maybe as getting a clearer, more organized view of the most important landscapes on your chemistry final exam map.
Yeah.
You've already done the hard work of gathering the information. Hopefully this deep dive helps solidify the connections and the core concepts.
Absolutely. You've definitely got the key tools and concepts laid out now from your materials. And, as you review this stuff and really connect these ideas in your own mind, here's maybe something interesting to think about. We've seen how fundamental principles, like, say, VSEPR theory determining molecular shape or the octet rule driving bonding, apply consistently from the simplest molecules all the way up to complex biochemicals. What other seemingly simple chemical idea that we talked about, maybe something related to dynamic equilibrium or perhaps thermodynamics and energy flow, might have equally profound but maybe unexpected connections to the intricate processes happening all around you in the world or even inside your own body right this minute?